Okay, let's talk about Euclidean domains a little bit. Euclidean domains are even more special than principal ideal domains. So remember, we will have the implications. An Euclidean domain is a principal ideal domain, and a principal ideal domain is a unique factorization domain. And these are basically rings in which division with remainder works. The Euclidean algorithm works. So here's the definition. A domain is always commutative, always with 1. Is called an Euclidean domain. ED, let's abbreviate. If there exists a function this function is sometimes called a Euclidean valuation from the non-zero elements of this ring to non-negative integers such that so this nu is going to give me a measure of the size of an element of the ring in some sense, such that given any a, b in R with b non-zero, there exists, so let's write it what we get. Given any a and b in R with b non-zero, you can divide a by b and get a quotient and a remainder. You can write a equals b times q plus r for some q and r. So there exists q and r in R such that a is bq plus r, and either r is 0 or its size is less than the size of the thing that you divided by. So either nu of r is less than nu of b, or r is 0. Okay. And so the first result would be some examples. Z is ED with Euclidean valuation being the magnitude of the number. So if you give me a number a and a number b, I can divide and get a quotient and a remainder. Maybe let's try again. What this is saying is that you have this function nu from non-zero integers to non-negative integers, sending a number to its size, nu n equals absolute value of n. If you give me a number and another number, I can divide and always get a quotient and a remainder, and the remainder always has size less than the thing that I divided by, or the remainder is 0. So this also works for negative numbers, by the way. Even if you give me 13 and minus 5, we did not talk about dividing by negative numbers before, but you can see I can still write it as like that, for example. And again, the size of the remainder is less than the size of the thing that I divided by. Yeah. So the Euclidean algorithm basically tells me that Z is a Euclidean domain with nu being the size. Example 2, polynomial ring over a field is Euclidean domain with nu of a polynomial being the degree of the polynomial. So here f is a field. And again, the proof is division with remainders, literally. Maybe one new example, Zi is an Euclidean domain Zi means, remember, this means all numbers of the form a plus bi, where a and b are integers, with nu of a plus bi equals s square plus b square, the size of the complex number, the norm of the complex number. So we know part A and part 1 and part 2 already. These follow from division algorithms. In these two rings, respectively. We haven't talked about the division in this ring. Maybe we'll do it after a while. Another example would be z join e to the 2 pi I over 3. Yeah, but these are rather rare. I mean, okay. The theorem that I want to state, pretty much the only thing that I want to state about them, maybe this we'll prove in a little bit. We'll play with zi a little bit maybe in the next video. Let me state the theorem that I want now. That every Euclidean domain is a PID. And this is basically generalizing the proof, how you proved that Z is a PID and Fx is a PID. If you look at those proofs, that really gives you a more general version. But I'll still write it out. So generalize the proof that works for these two cases, Z and Fx. So let R be a Euclidean domain. So I have this function nu, right? So have this function nu from non-zero elements to non-negative integers satisfying our property. And now take a what do I have to show? I have to show that it's a principal ideal domain. So you take a non-zero ideal and you try to find a generator. Let I not equal to 0 be an ideal. I need to find an element in I such that I is simply all multiples of that element. And which one do you pick? You pick the element which has least possible value of nu. So choose B in I minus 0 such that nu of B is minimal. Among all non-zero elements of I. So look at all the non-zero elements, look at all their nu values and pick one. So the nu values are non-negative integers. Among a bunch of non-negative integers, by well ordering you always have a least one. Choose a B which has that least possible nu value. And I claim that I is just the ideal generated by B. And how do you do that? Of course, B is in I, so the ideal generated by B is contained in I, that's clear. So now take some A in I, and then by the Euclidean domain property, write there exists Q and R in the ring such that A equals BQ plus R, and either R has less valuation than B or R is 0. Now notice that A minus R is a multiple of what do you want to say? Oh, no, let's just look at R. Note that R is A minus BQ, and both A and B are in the ideal I, right? A is in the ideal by choice, B is in the ideal by our definition of B, so this is in I. But then B was the element of I that has least possible new value. But this R has even lesser new value, so R has to be 0. Since B has least possible value of new for among, it's a new value, among all non-zero elements of I, we cannot have R is non-zero. If R was non-zero, then R would be a non-zero element of I which has even lower new value. We must have R equal to 0. And that shows A is BQ. So that's in the ideal generated by B. What did we argue? We took some element in I and argued that it's a multiple of B. So I is a subset of B. So I is B. So every ideal, non-zero ideal is principal. So every ideal is principal. So this is a perfect illustration of how proofs generalize. You saw these two proofs, the proof for Z and the proof for Fx, and it looked like they were exactly similar proofs. So what you needed was this definition. Once you have this definition, general definition, you see that you can sort of generalize these two proofs into this more general proof, and then those two become special cases of this. And then, by the way, once you know that every Euclidean domain is a PID, then you know that it's a hence a UFD. So now you know that unique factorization into irreducibles hold for all these rings, all these 3 rings, for example, and you got a uniform proof of that. You know that the notion of GCD makes sense, etc. So unique factorization into irreducibles hold in Euclidean domains. Primes are maximal, non-zero primes. Non-zero prime ideals in Euclidean domain are maximal. This we knew was true in any PID. GCDs make sense. GCD exist and can be found by Euclidean algorithm, can be computed like you computed them in these two examples, in Z and in Fx, by repeated division by using Euclidean algorithm. So all these things go through in general. Okay. So next time we'll work with this third example a little bit.